Hello Bio242! This short video will cover details on the structure of the pancreas and its endocrine functions. I will also talk a bit at the end about other organs of the body that produce hormones, although they are not primarily endocrine glands. The pancreas is a roughly tadpole-shaped organ located behind your stomach. It's tucked into the curve of your duodenum, the first region of your small intestine. The pancreas is a mixed gland, meaning that it has both endocrine and exocrine functions. The majority of the cells in the pancreas are acinar cells. These cells produce enzymes that break down lipids, carbohydrates, and proteins in your digestive tract. This is the exocrine function of the pancreas. The endocrine cells of the pancreas are found in the islets of Langerhans, also known as the pancreatic islets. They serve primarily to regulate your blood glucose levels. Here we have a cadaver dissection showing where the pancreas is located. Here's the diaphragm. The liver and gallbladder are up here. They've been dissected apart so that the pancreas is easier to see. The stomach and intestines have also been cut away to show the pancreas. See what I mean about it being tadpole-shaped? The two cell types found in the islets that are mainly responsible for controlling your blood glucose levels are the alpha and beta cells. Alpha cells produce glucagon, a hormone that raises your blood glucose levels. Beta cells produce insulin, a hormone that lowers your blood glucose levels. The islets also contain delta cells that produce growth hormone inhibiting hormone. Growth hormone inhibiting hormone, produced in the pancreatic islets, acts as a paracrine factor to suppress insulin and glucagon secretion by the alpha and beta cells. The islets also contain F cells that produce pancreatic polypeptide. Pancreatic polypeptide inhibits gallbladder contractions, controlling the release of bile into the small intestine. Although all four cell types are found in the pancreatic islets, we're going to focus primarily on the alpha and beta cells. This slide shows the balancing act that insulin and glucagon do to keep your blood glucose levels within the normal range. When blood glucose levels rise after a meal, your pancreatic beta cells release insulin. Insulin tells the cells in your body to take in that glucose and use it. As cells take up the glucose, your blood glucose levels fall back down to the normal range. When it's been a while since you ate and your blood glucose levels are falling, your pancreatic alpha cells release glucagon. Glucagon tells your liver to release glucose into the blood, bringing your blood glucose levels back up to the normal range. One way your body deals with glucose is to store it as glycogen. Glycogen is a huge polymer made up of hundreds of glucose molecules strung together. When insulin is released, insulin tells your liver to take up glucose and use it to make glycogen. In effect, your liver is storing glucose for later. When glucagon is released, your liver takes some of that stored glycogen and breaks it back down to glucose. That glucose is then released into the blood. This slide summarizes some of the details about glucagon: what cells make glucagon, what glucagon does, how glucagon does it, and how glucagon is regulated. Glycogenolysis is the breakdown of glycogen into glucose. Gluconeogenesis is the formation of new glucose molecules from lactic acid, amino acids, or from glycerol. This is another way by which the liver produces glucose for release into the blood. Hyposecretion and hypersecretion of glucagon are rare, although high glucagon levels may contribute to the symptoms of diabetes mellitus. This slide summarizes some of the details about insulin. As in the previous slide, we have what cells make insulin, what insulin does, how insulin does it, and how insulin is regulated. Hyposecretion of insulin causes type 1 diabetes mellitus. Hypersecretion of insulin is usually only seen as a result of type 2 diabetes mellitus, but in that case, the body is resistant to insulin and so cannot respond to the high insulin levels. Diabetes mellitus is a very significant health concern. The Centers for Disease Control estimate that nearly 26 million people in the U.S. have diabetes, and that's just the ones that have been diagnosed. There are two forms of diabetes, type 1 and type 2. Type 1 diabetes is hypoinsulinemia, or hyposecretion of insulin. Type 2 diabetes is caused by insulin resistance. In type 2 diabetes, the pancreas continues to produce insulin, but the cells of the body can't respond to it. This type used to be called adult-onset diabetes, but is becoming more frequent in children and adolescents. Type 2 diabetes is associated with obesity. Despite the two different pathways and their different causes, both types of diabetes lead to high blood sugar levels, hyperglycemia. The high blood sugar levels lead to the classic symptoms of diabetes: polyuria, which is excessive urination, polydipsia, which is excessive thirst, and polyphagia, excessive hunger. If left untreated, high blood glucose levels can damage the blood vessels and nerves, leading to blindness, ulcers, numbness, foot amputation, and even coma. The main endocrine glands that we've talked about in detail in class and in these videos are the pituitary gland, the thyroid, the parathyroid, the adrenal glands, and the pancreas. But there are a number of other organs that produce hormones as well. The gonads, the ovaries and testes, become highly active at puberty. They produce hormones that regulate sexual maturation. The ovarian hormones also regulate the menstrual cycle. We'll talk about these more when we get to the reproductive system. The pineal gland produces melatonin. Melatonin regulates our body clock. Levels are low during the day and rise at night, making us drowsy. Some people take melatonin to treat insomnia or jet lag. The heart produces two hormones that lower blood volume and blood pressure: atrial natriuretic peptide and brain natriuretic peptide. BNP was named brain natriuretic peptide because it was originally identified in pig brain, but it is, in fact, made by the heart. Both of these hormones increase sodium excretion, increase urine production, reduce thirst, block release of antidiuretic hormone and aldosterone, and trigger vasodilation. That is, the increase in diameter of your blood vessels. The GI tract, your gastrointestinal tract, has a number of cells, the enteroendocrine cells, scattered throughout it that produce hormones that regulate digestion. We'll talk about these a bit more when we get to the digestive system. The skin produces a precursor to vitamin D. The skin produces cholecalciferol with exposure to UV light. It's then activated in the kidneys and helps with calcium absorption in the small intestine. Adipose tissue produces a hormone called leptin that acts on the brain to suppress appetite. People who are born with a mutation that keeps them from making leptin eat enormous quantities and become very obese. When you diet to lose weight and reduce the amount of adipose tissue on your body, you reduce your leptin production as well. This is one reason why keeping weight off can be problematic. The kidneys produce several different hormones. Erythropoietin is released when blood oxygen levels fall. Erythropoietin triggers red blood cell formation so that you can carry more oxygen. You may know it better as the sports-enhancing drug EPO. If you increase your red blood cell numbers, your blood gets better at carrying oxygen, and you may see an improvement in your athletic performance. Renin is triggered when blood pressure or volume fall. Renin triggers the release of aldosterone and antidiuretic hormone. So ultimately, renin release leads to increased fluid intake and retention, which brings blood pressure and volume back up to normal. Calcitriol is the active form of vitamin D. When cholecalciferol is made in the skin, it travels to the kidneys and is activated to calcitriol. Calcitriol then increases calcium absorption in the intestines. This slide summarizes how the kidney hormones are stimulated and their effects. On the left, we see how the kidneys affect calcium absorption. Sunlight triggers the formation of cholecalciferol in the skin. Cholecalciferol is activated in the kidneys into calcitriol. Calcitriol then circulates to the digestive tract where it stimulates calcium absorption. On the right, we see the effects of the kidneys on the blood. Falling blood oxygen levels triggers erythropoietin release, which increases red blood cell production. Falling blood pressure or volume triggers renin release. Renin activates angiotensin. Angiotensin activates aldosterone and antidiuretic hormone. Our kidneys hold on to more water, we feel thirsty and drink, and our blood pressure comes back up. The endocrine story of the pancreas is all about blood sugar homeostasis. Your pancreas works very hard to make sure you have enough glucose, but not too much. You can read more about the pancreas on pages 620 to 623 in your textbook. There's even a full-page spotlight on diabetes mellitus. For many of the other organs mentioned, we'll revisit them when we get to their organ system. For now, you can read more about the pineal gland on page 619 and the other organs on pages 624 to 626.